All right, guys, welcome to another episode of CUDA Education. Today, I want to just tackle one important aspect of this compute colon load script. Okay, and it's a very nuanced thing, but it's very important for us to get a better understanding of what's going on with this algorithm. Um, So let us just run the algorithm and see what's going on. Okay, so as always, guys, we have our instances of these objects, and we have a certain level of detail, and we have a bunch of objects, all these objects, right? We have to now pin down what buffers are at play here, right? And there are really three buffers that are at play in this algorithm. Okay. um Before we get into that, let's just talk a little bit about how these things are built and how it's displayed and laid out. Okay, so each one of these objects is made up of meshes, right? And the meshes are a series of triangles that are basically pasted together so that it creates the object, right? So we have a mesh that basically creates the object. Right now, for the objects that are closest to us, of course, we have meshes that are highly detailed. What that means is that there are many triangles in that mesh. There are many, you know, it's very detailed. The contours and the features are very clear on it. And when we go down to the lower detail stuff, like if we just go all the way down to the lower detail stuff, we see that there's less detail, right? And it's less detail because it's less triangles in the mesh. It's less data, less vertices, less indices, all of that good stuff, right? So we inherently understand that. Okay, fine. So we know that the more triangles, the more intricate the mesh is. The heavier the data, of course, and the more detail we see in our rendering our object, right? We understand that. um, so there's building the actual object itself. There is then, now after you build the object, you have to position the object in sort of our scene, right? So we have our object here, and then we're trying to position it within the scene, right? So think of it as sort of, you have a factory that makes cars. Okay, so you have a factory that makes cars, and the factory is in one part of town, and it makes the cars, right? But then you have to ship the cars to specific locations, in your country or in the world, right? You have to ship the car to that specific location, right? So the way I kind of internalize it is that I have a factory right here. I build the object, and then I place the object, wherever it needs to go. Now, if I'm building an object for down here, obviously I am I'm building this red object. I'm not building this green object, right? So I build the red object, and then I ship it all the way down to back there, right? And of course, the logic being in this script, as we know, is that the further away the object is the less detail we give it, because it's the less ability we have to appreciate, what's going on down there, right? We care about what we see in front of us. We don't necessarily care about what's going on way back there, right? So we save the processing power and the burden of doing a fully detailed object all the way down there, because we literally just don't care about it. We care about what's in front of us right here. All right? So let me repeat. We build the object with the appropriate mesh using triangles, right? If it's a highly detailed object that we're trying to build, we definitely have more triangles. It's the mesh is very intricate, and we take on the burden of that to build the object highly detailed. If it's a lower detailed object, we skimp on the number of triangles in the mesh. The mesh is less detailed, and we certainly reap those savings, and we ship the object all the way back there to like the red objects, because that's its rightful place. So we have the mesh, we build the mesh, and then now we also ship the mesh to a specific location in our scene, okay, or in what we're rendering. There's also this thing of scale. So, is this object that we're building normal size? Is it double its size, or is it shrunk? Is it half its size? There's also this element of scale. We're gonna add the scale element to we're gonna associate the scale element to sort of the position element. So what I mean is that we have a struct called instance. We have a struct called instance, and that deals with what position does the object live, and also what scale it is. Right now, for our intents and purposes, the scale is uniformly applied to all objects, right? So the reason why this object right here looks smaller is not because it's a smaller scale, it's just because it's visually farther away from the screen. So as far as I'm concerned, the object, it's all. So if you have a scale of 1, it's all the objects are 1. If you have a scale of 2, double, all the objects are double its size, etc., etc. Okay, so we have a strut called instance where we have position data, so x, y, and z, and then we also have scale as part of the as part of that instance strut, or that instance buffer. Okay, so that explains instance. So instance is position of the object in the world and also its scale. Okay, so we have now explained instance. We still have to talk about actually building the singular object itself, right? To do that, we use vertices, right? So the vertex buffer, right? So the mesh is basically built using vertices, and vertices basically build the mesh, and that's what is the raw low level data that's used to build the object, right? To build up the mesh which builds the object, right? Vertices. Now, as I've explained in previous videos, we have a hack in order to save data and to save sort of the mechanics of managing all these vertices. Because remember, these vertices, especially for the high detail ones, for the high detail objects, the vertices, aka the meshes, it's a lot of triangles. It's a lot of vertices in the mesh in order to make this highly detailed object. So because there's a lot of vertices in the mesh to make these highly detailed objects, we have to it's a lot of data to splash around. So we have a hack where instead of sloshing around and moving around the all the vertices, right? We instead we apply labels to the vertices, and we just um, we just we just we just use that label. So the vertices might be 2 or 3 digits, but we use instead of using the 3 digits and sloshing around the 3 digits to sort of build the object, we just we use a label which might be 1 digit, and then we know that that one label really means, it's like a mask, or it's like a nickname for what the actual vertice is. So think of the best way I could describe it is, think of someone who has a nickname. So they have a nickname and they have a government name. So your government name is your first name, your middle name, and your last name, right? It's a long name. Let's say you have a long name. Alexander Johnson Michelangelo is your long name, right? But then we just call you by your nickname. We just call you, instead of every time we see you, we call you by your long government name, we just call you Alex. That's your nickname. Now, we have a cheat code where we say every time we say Alex, we know we mean Alexander Johnson Michelangelo, right? So instead of using the long name, we just use a nickname, and we all agree that that nickname means that nickname Alex means Alexander Johnson Michelangelo, right? So that's the first sort of efficiency gain that we have. So instead of, every time we have to point to that vertice, instead of it being Alexander Johnson Michelangelo, every time we just use the word Alex, right? The other thing is that when we repeat vertices for each one of the triangles, so let's say for 3 triangles, they all use this one Alexander Johnson Michelangelo point, okay? So you don't want to be repeating Alexander Johnson Michelangelo 3 times in your data. You just want to say Alex, right? So, for all 3 datas, you just point to that. You just say Alex for all 3 of them, and you save. So not only is it easier to manage just with the label, but when you repeat vertices, it's also easier to manage because you're just using the shortened nickname, and it's easier to manage when you're trying to move around and manage. Because remember, 10,000, 20,000 vertices, these things have to be managed in memory. It's not a trivial matter, right? It explodes very rapidly the more intricate your object becomes, right? So we have the vertex buffer, which is the vertices, which is the long name, Alexander Johnson Michelangelo. Then we have the index buffer, which is the indices, which is just like Alex, the person's nickname, right? So the vertices and the indices are charged with managing the object itself, building the singular object itself, right? Doesn't care about where this stuff lands in the world space. It doesn't necessarily care about the scale of it, right? It's just building the object, right? Now, real quickly, let's just talk about scale since it's irrelevant. So, if you're scaling up, for example, doubling the scale of the object, then you basically just I guess you double the distance of the vertices or the indices, what have you. You basically, so instead of it being 1 unit length away, it's now 2 unit lengths away, and all that stuff, right? It's just you're modifying the mesh to expand if you're upscaling, or to shrink instead of it being 2 because you're doubling, if you're halving, that same one distance, unit distance, is now half, right? So you're either expanding or shrinking with the scale. But as far as the vertex buffer and the indices, the index buffer, the indices buffer, it just cares about building the object as requested, and it builds the singular object, right? It doesn't care about world space. It's like you're building the car in the factory, right? And you just build the car in the factory, and then someone else, the delivery and logistics people, are in charge of shipping that car into its appropriate place in the world. Okay, so once we have the object and it's complete, let's say it's not a green object, but it's a red object. Now let's say this was a red object. Now after we build the red object, now we got to ship it to all the way back there, right? Because of course we're building many objects and they need to go somewhere. So we build the red object and then we ship it all the way back there. Now, when we ship it all the way back there, that's a different department, right? So we're not dealing with vertex buffer and index buffer, vertices and indices. We're now dealing with the instance part of the equation, right? So the instance part of the equation, again, deals with where does this object land in world space. So we take this object and then we push it to move it to where it needs to be in world space. You know what's an interesting thing that you could think of, that's a similar analogy? Think of like when they're building windmills, okay? So if you're building windmills, you don't build the wind, and then let's say the eventual location for this particular windmill that you're building is out in the depths of way out at sea, right? Way out at sea, where you can't even see it from land, right? You don't build the windmill out in the middle of the ocean. You build the windmill in the factory and then you ship it out. And now it might be a big process. There might be big trailers and all that stuff to manage it, but you then ship it out to the middle of the ocean, right? Because it's just more efficient to do it that way. Well, that's a similar thing with instance data. So the instance data now is pushing the object to where it needs to be. It's delivery and logistics in world space, right? That's the way I look at it. So you're pushing the object now all the way to where it needs to be. So again, if it's a red object, it's going all the way back there, right? Because that's what the instancing is in charge of. Now I say all these things because we have to get to, we need to really understand what's going on with this input state stuff, right? So I guess we'll get back to this, but I do want you to just internalize all that I've said. So we have the vertices and indices, which are in charge of building the singular object, and then we have the instance data, which is involved in moving that object to its final destination, right? So let us now look at some data, some notes that I have that sort of helps us to understand what's going on. So as we said, the vertices and the indices, they are in charge of building the singular object. Okay, so we're building the singular object, right? The instance data is involved in moving the object into world space, right? It's a very nuanced thing, as I said. It looks simple here, but like you really need to understand it, because all of this stuff is, and these are thousands of vertices and stuff, right? This is happening behind the scenes in the computer on your machine, right? So you need to basically internalize, right? So indices and vertices, these are in charge of building the singular object. Instance is placing the object in world space. And of course we have our X and Y. I really should have had a Z too, because whatever, there is a Z of course, but to simplify the vertex and indices, we just we just do we just do X and Y, right? And, you know, notice that point 2, which is 0, 1, is 2 digits here, right? And 0, 1 is repeated multiple times in our data. So you have 1, 2, 3, 4 integers that you have to remember, whereas in the indices version, you basically just have to remember two integers, two numbers, right? So that's what I was saying. When you repeat the data, it's easier to remember Alex and Alex as opposed to Alexander Johnson Michelangelo and Alexander Johnson Michelangelo, right? That's like a whole lot more data to remember as opposed to just Alex and Alex. Now, you know, obviously we know we have made an agreement that Alex basically means Alexander Johnson Michelangelo, but we're not, you know, we're not going to press the point here, right? And when we're managing the indices, right? We're only going to resolve it to its basic full government name or its full, you know, data location when it's absolutely needed. Otherwise, we'll just run with Alex for now. Okay. So, right. So this is building the singular object, right? And then now the instance stuff is about after we build the singular object, now we ship it out to because this is the mesh. This is the mesh for the singular object, and then we ship it out to its appropriate location in our application. Okay. So notice that in the instance object we have x, y, and z, which again is position coordinates. So again, we're dealing with position coordinates, but it's not the same coordinate system for the object itself. It's now world space, right? That's what these computer graphics guy. We're talking about world space. So it's not the same x, y, and z. It's like the world space, right? It's we're talking about, you know, coordinates relative to the entire scene and the world application. We're not necessarily talking about, you know, building a single object. Now we're talking about the world space. Where is this red object that we built gonna land? And it's gonna land somewhere down there because that's where it's supposed to be, right? So we have x, y, and z coordinates, and then we also have this scale. We have this scale object, which in our application we'll see that 1f 1.0f is for just normal scale, right? But we could upscale or downscale the object as need be. Okay, so again, instance object is supposed to move. It's the shipping and logistics. It's supposed to move our object now that we have fully created to its final destination. Just like in cars, you build a car in the factory, but then you have to ship the car to the purchaser of the car. You have to ship the car to the person that bought the, you know, that paid for the car, right? So it's a similar thing here, instant stuff. Okay, so what I want to do is play around with this exact concept here. Now, just to do the easy stuff first, let us go look at scale, right? So scale is actually 2. Okay, or is it 1? Is it 1 or 2? Okay, so we have scale at 2, right? So let's do scale at 0.5, right? 0.5, right? So let us close this and let's rerun our application with, I did this in a previous video, but it's relevant now, just so you guys follow along. So as you can see, I didn't change anything. As you can see now, the objects collapse, right? Because we have now in our instance data changed the thing to a different scale, right? And again, it's instance data, right? If we upscale to 4, we are going to get bigger stuff, right? So these objects are now it's destroying. You know, we could see exactly what's going on, right? You know, we could see what's going on, right? So let us get back to normalcy. So actually, it was 2. That was the correct thing, and it makes sense for what we're talking about here, because the instance data is responsible for the scale stuff, right? So let's go back to normal. Just make sure that we have always put things back to the way it was before, so that you don't you know, you don't mess up yourself the next time around when the object doesn't run the way you expect, and you don't the application doesn't run the way you expect, and you don't understand, you don't remember what you changed in order for it to not run the way you expect, right? So we're back to normal. All right, so that is our scale situation. Right now, what gets a little interesting is so we have to read so we now of course, you know, we have our vertex data and we have our instance data, right? So the thing is that vertices and indices basically you know, when you're building an object, you run through all of the vertices for that object, right? So the object is a very you know, the object is a very, let's say for the high detailed one, it's a very detailed object, and we have to build, you know, we have to run through all these vertices, 10,000, 20,000 vertices in order, or a lot of indices in order to get our object, right? But when we get to right, so we have to go through a lot of vertices and stuff in order to get our object. Um, um, but for this one object that we're building, the instance stays the same. The instance stays the same. So we run through all of this data for the vertices, because it's like 10,000 vertices, right? But the instance stays the same. So this is instance 1, this is instance 2, this is instance 3, this is instance, you know, 276, this is instance maybe 275 or something, I don't know. This is instance 138. I don't know what the arrangement of the objects are, but for all of these vertices that we're processing, we're processing it for one instance, right? And this is what this data right here is trying to say. It's like, you know, instance data at per instance rate. All right. So for each one of these vertices, that we're dealing with, the instance, you know, it's you know, the instance stays the same, okay? But then what happens is that, you know, we could corrupt this and say, okay, instance data at per instance rate. But we could say, okay, we don't want instance data on a per instance rate. We want instance data on a per vertex rate, right? And what do you expect to happen if we change it from, you know, a per instance rate, right? So remember, all of these objects are instances, but you know, there are way less instances than vertices. There's like a whole bunch of vertices, and the vertices are, you know, it's a lot of vertices, right? But like what I'm trying to intellectually understand and communicate is when we change this instance data at per instance rate, right? So each one of these are instances, and it's instance data, right? It's instance data at a per instance rate, right? But what if we now change? What if we now change the instead of it being a per instance data, we go to a per vertex data, right? And remember, a per vertex rate, right? And remember, um, remember that our vertices data is way longer than the instance data, right? I mean, I know it looks like there's a lot of instances here, but it's nothing compared to the 10 or 20,000 that we're doing uh, um, for each individual object, right? So the $1,000,000 question is, what happens when instead of it being per instance data at per instance rate, we change it to the we take the instance data, but we do it per vertex or stuff like that, right? What do we expect to happen, right? And I mean, it's kind of like, oh no, I'm sorry, I gotta close this out first. I gotta close this out. Okay, so what happens when we change to per vertex, right? We get a whole bunch of jumbled garbage, right? And basically what happened is that the instances are like scattered across several different vertices or something like that, but yeah, as you can see, it's a jumbled mess, right? Because we're not doing instance data correctly, right? And you can see that your frame rate is like atrocious, right? So I say this because we kind of need to understand, anchor us in what's going on. Now, if we go back to our per instance data, the per instance rate, we get back our normal objects, right? Now the thing now is let us do the opposite error. So we're taking mesh vertex layout description at per vertex rate. So we are there are many vertices to make one thing, but instead of moving the read per vertex, we're now moving it per instance, right? Which is it would be a lot slower cadence because there are way less instances than vertices. So what's gonna happen is, let's see what's gonna happen. Basically, basically we don't see anything, but really what's happening is that and literally, like, we really don't see anything. Like, no matter what you're doing, we really don't see anything. Now remember, these things are calculated mathematically. We are dealing with here the rendering portion of it. So there's a rendering and the mathematics of it. So the the uh the uh the GUI, the user interface, is gonna still count all the objects and stuff, even if we can't visually see it, because it's a visual thing that we're messing around with, right? But also notice that the frame rate doesn't collapse, right? So anyway, the logic is that all of the because the it's a whole bunch of vertices, but they're all assigned to basically a handful or the same instance. Basically there's a collapse. There's a collapse. They're all basically being assigned to the same point. If you guys in the comments can better verbalize what's going on, I'd appreciate it. But basically everything is being assigned to the same instance, right? And literally it's going through all of the instances and it's basically applying it to like one object or one thing. I don't know. I can't fully like explain it, but when we go back and we run again, we get everything back in order. But even more importantly than us messing with the rate of how the data is read, what I do want you guys to fully understand is really, and really the point of this video is just to understand that the vertices and the indices relate to building the actual mesh of the actual object itself, and then the instance is pushing that object into the proper world space. Now, there's another portion that I is really important that I want you guys to understand. So, another dynamic. Now, if we, if I gave you this application and said, okay, I only gave you vertices and instance data, would you be able to create what we have here? If I only gave you the vertices and the instance data, would you be able to create this thing? Right? Now, obviously, there will be some disadvantages and downsides. There's no indices, there's no index data. Would you be able to create this application? And the survey says, yes, you would still be able to create this application, right? Because remember, you have the raw vertex data for each object, and you have the instance data, so you know where the object is located, right? So yes, you would be able to still create this application. You'd still be able to do it correctly, matching basically everything that's being done in this application. The only thing is that it would be less efficient in terms of a data management perspective, because you wouldn't have the advantage of the indices, right? So you would be sloshing around a whole lot more data and the repeating data, which is like heavy lifting and a lot of RAM and system resources and stuff. So you would be able to still create your application. It would be less efficient, but you would still be able to do it. Okay? Now let's go a step further. If I gave you only indices and instance data, would you be able to create what we see right here? Would you be able to create what we see right here? If I only gave you indices and instance data, would you be able to create what we have here exactly as it is? And the survey says the answer is absolutely not. You would not be able to create what we have here at all. And the reason why you wouldn't be able to create what we have here is because you don't know what these indices actually represent. You have no idea what the vertices or the vertexes are. You just have a bunch of labels. So it's like you know Alex, but you don't know what Alex's real government name is, right? So you just have a label. You just have an Alex, but you don't know who Alex really is. You don't have his government name, right? So you will not be able to create the application if you just had indices and instance data. Okay? So the last one is if we had indices and vertex data, would you be able to create the application as it is now? If you only had indices and vertex data, would you be able to create the application as it is now? And the answer is No, you would not be able to do it. And the reason you wouldn't be able to do it is because you wouldn't know, first of all, you wouldn't know where the object goes. Like, okay, I built the object, but I have no idea where it goes. That's the first problem. The second problem is you don't know at what scale. So you don't know what scale the object is supposed to be at. You have no idea. So you just have a bunch of objects and you don't even know the number of objects that you need to build, right? Because you don't know the number of instances. So you don't know the number of instances, you don't know the number of these you have to build. You don't know the scale, whether you want it really big, really small, or whatever. You don't know the number of objects, you don't know the scale, and you don't know the layout of the objects, right? You don't know where they go. You don't know the number of objects, you don't know the scale, and you don't know what the layout is of the objects. Like, what if I just wanted one single row of instances, right? You wouldn't know because you don't have the instance data. Okay, so yeah, guys, it's a very nuanced thing, and you really have to understand what's going on in the background. Again, just to be thorough, guys, that the level of detail is basically related to the indices, right? So these numbers represent the indices. So that, like, for the highly detailed objects, you get way more indices, and for the lower detailed objects, you get less indices, right? But again, guys, you need to resolve these numbers to vertices, right? Because vertices is actually the raw data, right? But we use these numbers, we use these indices, we use these numbers to just be able to efficiently manage the manage the data. Like, for example, you see that the number 5 is used here, here, right? The number 3 is used here, and here, right? So repeating gets easier when you use the indices. So this is my attempt to understand vertices, indices, and instance data. And if we look in instance, if we look at the instance stuff, we'll see that right, we're putting yeah, we're basically deciding the location of objects here. Let's tinker with this actually and see what happens. So if we do so if we mess with the instance data, we could see that now we get a whole different layout, right? You get a whole different layout, and I haven't frozen the Frustrum or anything, so I'm not culling anything. You get a whole different layout, right? Because the instance data is now changed, right? So if we do Z here instead and we run it, we're gonna get another layout again, right? Where is the stuff? Is it anywhere? Okay, yes, it's there. Okay, right, so we get a whole different layout again, right? And let's say we do X here. Let's say we do X here, right? So we get a whole different layout again, right? So I'm not gonna explain whatever, right? But you guys get the drift now, right? So instance data, it's a very thing. Yeah, but anyway, guys, we have got to make sure we get back to baseline, right? So we are back to what we were talking about before. We understand the whole thing, right? So that's instance data, I don't even know if I could really mess around with the vertex data, but yeah, but all right, guys, I think that's enough for this video. So anyway, guys, if you want to to be able to run this stuff on your machine, number one, you need a Windows-based machine. Number two, you need a Vulkan-capable GPU. And then number three, if you want to run the ray tracing examples, this example is not ray tracing, but if you want to run the ray tracing examples, you need a ray tracing capable GPU. I know for NVIDIA, it's RTX and above. Don't know about Intel and AMD. Now, if you have a choice between which GPU to do, simply because some of the tools that I use Insight Graphics and I use Insight Systems. Those only run on NVIDIA GPUs. So if you are, if you want to follow along, exactly and do the things that I do in this video, especially when I use those external tools, you want to get an NVIDIA GPU. Now, the thing is that Insight Graphics is a graphics debugger. So that's like going into the weeds and figuring out when your application isn't behaving properly and you need to know why it's not. So that's the Insight Graphics. Insight Systems is for profiling your application. So when your application is running slow and you want to optimize it to run as fast as possible, Insight Systems helps you to do that. But again, those tools are for NVIDIA GPUs only. And that's about it, guys. I think this was a good video. You guys fully understand now vertex data, index data, and instance data, right? What they call buffers. These computer graphics guys, they like to use the word buffers, right? And you kind of get a good understanding of what's going on. I am not sure what else I want to tackle with this algorithm, but stay tuned. You will know. But we have spent some time on this, and we have gotten a lot done with it. I think I get a comfortable grasp of exactly what it's talking about. I think the indirect and instance stuff, because we dealt with the shaders, was pretty cool. Yeah, there's probably more stuff like this indirect and instance pipeline. Like I haven't dived into this, so maybe I will dive into that just to finish off this algorithm, and then we will move on to the next algorithm. So anyway, guys, we are on the cusp of a brand spanking new year, 2026. So please think long and hard about how you want to spend your time in 2026. What things you want to achieve, what goals you have, how can you improve yourself, both personally, professionally, and in every other dimension, health-wise, all of that good stuff. Take advantage of the new year. Time is expensive, so you want to use it wisely. And you want to be a better version of yourself than you were in 2025. So think long and hard about how you want to attack the new year. And once you set out the plan, try your very best to stick to the plan. Okay? Time is expensive and nothing can be taken for granted. So be happy that you're here and be happy that you could watch CUDA education videos, of course. And we continue on our journey. Definitely want to keep up the pace and just really get us learning computer graphics and a bunch of other stuff. I have some surprises for you guys that will be coming up, so stay tuned. Obviously, tell your friends, get a group of your friends who are maybe artistically inclined or are interested in programming or are interested in computer graphics or are just interested in personal development, learning how things work, introduce them to the channel. Like, subscribe, you know the good stuff. If you guys have a better way of communicating how changing the per rate, how changing the per rate changes how we visually see stuff, please feel free to add in the comments below. Have a New Year's, guys. Merry Christmas. Have a great day. Goodbye.